So we're addressing hypotheses about a population mean when the population standard deviation, sigma, is known. There are two approaches for determining whether or not to reject the null hypothesis: the critical value approach and the p-value approach. Let's first discuss the critical value approach. With the critical value approach, we determine the critical value, or that level of evidence beyond which we're convinced that we should be rejecting the null hypothesis, based on some value of alpha. Then we compare the test statistic to that value. The steps in the critical value approach are as follows. We'll apply these steps to hypotheses dealing with the population mean when sigma is known, but these steps apply to all statistical hypotheses. First, we state the null and alternative hypotheses. In this case, we set up H0 and H1 to deal with the population mean, mu, and the hypothesized value of the population mean is mu0. We have three options for hypotheses depending on what kind of question we're wanting to answer. The null statement could be strict equality, with the alternative being strict inequality. We could have greater than or equal to in the null, with less than in the alternative for a lower tail test. Or we could have an upper tail test with less than or equal to in the null and greater than in the alternative. Second, based on the population parameter we're addressing in the hypotheses, we select the appropriate distribution to use for the test statistic. When addressing population means when sigma is known, we use a z-distribution for the test statistic. Given our discussion of confidence intervals, you might imagine that we'd use a t-distribution for the test statistic when addressing population means when sigma is not known, or a z-distribution when dealing with a proportion, or a chi-square distribution when dealing with a variance. We'll eventually get to those examples, but identifying the appropriate distribution is an important step. Third, we determine the rejection and non-rejection regions and their associated critical values. That is, we decide what level of confidence that we want to use to draw conclusions about the hypotheses. Much like with confidence intervals, typical options are 90%, 95%, and 99%. With what probability do we want to draw incorrect conclusions? What chance do we want to leave in the rejection region for there to be a type 1 error, the case where the evidence tells us to reject the null when we really shouldn't? And where should that rejection region be? Based on the first step, should the rejection region be in both tails, or just the lower tail, or just the upper tail? Fourth, we calculate the value of the test statistic. We'll talk about the test statistics for hypotheses for the other population parameters later, but for now, all we've discussed is the test statistic for hypotheses about a population mean when sigma is known. For this case, the z-test statistic is the difference between the sample mean, y bar, and the hypothesized mean, mu0, divided by sigma over root n. Fifth, we compare the test statistic to the critical value or values. Recall that the critical value is that level of evidence that defines the rejection region. Again, the test statistic measures how different the sample evidence is from the hypothesized value in terms of standard deviation units. If the evidence is a lot different, then the test statistic will land in the rejection region. That is, if the test statistic lies beyond the critical value, then it lies in the rejection region. Sixth and last, we make a decision. If the test statistic lies in the non-rejection region, then we don't reject the null and draw a conclusion about the null statement with our level of confidence. If the test statistic lies in the rejection region, then we reject the null and draw the appropriate conclusions. You're never finished with the statement, don't reject the null, or reject the null. What does it mean to reject the null? We're doing the statistical analysis in the first place to draw conclusions about a population parameter. And if we draw conclusions about the population parameter, there are larger ramifications to doing so. For example, if we conclude that the mean life of batteries is less than 3 years based on a sample, then that may have implication for warranties or for some design changes. We tested battery life for a reason, and our conclusion should deal with that reason. Let's go through these steps with an illustrative example. Let mu denote the true tread life in miles of a certain type of tire. A sample of 16 tires were drawn from a normal population with standard deviation 1,500 miles. With 90% confidence, we're interested in learning if the true average tread life is greater than 30,000 miles. The mean tread life from the sample was y bar equal to 31,000 miles. Let's follow the steps of the critical value approach to address this problem. First, the hypotheses. We're interested in learning if the true average tread life is greater than 30,000 miles. Greater than 30,000 miles. That statement doesn't imply equality. It's strictly greater than. So this statement must be in the alternative hypothesis. H1 states that mu is greater than 30,000 miles. The null hypothesis must contain an equality statement because equality is always in the null. So H naught is that mu is less than or equal to 30,000 miles. Second, we select the distribution. Here we see that we know sigma explicitly to be 1,500 miles. That is, the population standard deviation is known. As such, we know that when we're dealing with hypotheses about a population mean, when sigma is known, the test statistic will follow a z distribution. Third, we determine where the rejection region lies. This is a one-tailed test with the rejection region entirely in the upper tail, because a greater than sign appears in the alternative hypothesis. That is, we're going to reject the null if the evidence lies greater than the hypothesized value. To be convinced, the test statistic would need to lie in the upper tail. Also, we want to draw conclusions with 90% confidence. So alpha of 0.1 must lie entirely in the upper tail. We need to find the critical value on the z-axis, so we look for a tail area of 0.1. In the z-table provided in this course, we look for a probability of 0.5 minus 0.1, which is 0.4, between 0 and the value z. The closest we get to this value is z equals 1.28. So the critical value, that level of evidence beyond which we're convinced that we should reject the null, is 1.28. Again, another way to say that is, if the sample mean lies more than 1.28 standard deviations away from the hypothesized value, then we're convinced that we should reject the null with 90% confidence. Next, we calculate the value of the test statistic. We know we're using a z statistic. Z naught is y bar minus mu naught divided by sigma over root n. That's 31,000 minus 30,000 divided by 1,500 over root 16. The value of the test statistic is 2.67. That is, y bar lies 2.67 standard deviations away from the hypothesized value. In the fifth step, we compare the test statistic to the critical value. The critical value is 1.28. The test statistic, at 2.67, lies beyond the critical value. It lies in the rejection region. The evidence suggests that we should reject the null with 90% confidence. And so we make a decision. We conclude that the mean tread life is indeed greater than 30,000 miles. If the manufacturer wants to make a claim that the mean tread life of this brand of tire is more than 30,000 miles, then our sample of 16 tires backs up that claim with 90% confidence. So that's the critical value approach to drawing conclusions about a set of hypotheses. It requires alpha to be determined in advance, as that gives us the size of the rejection region. We'll change up this requirement when we discuss the p-value approach.